Composition of and inverse of functions. This first lesson is going to be the composition. In this lesson, you will be learning how to perform operations with functions, or reminded of operations with functions, and then finding the composite of two functions. As a language objective, we can say that you'd be able to describe the process to compose one function within another. Now, quick review, function notation. You have to know function notation. It's read f of x, where the function is defined in terms of x. Here, if we take a look at f of x equals 3x minus 4. This is saying this function is defined in terms of the variable x. Remember that f of x is the same thing as saying y. We use function notation for shorthand, because now if I say f of 2, instead of what is y when x is 2, I can just say f of 2. This means substitute 2 in for every x in the function and evaluate. So f of 2, I take this 2 and I plug it in for the x, so I get 3 times 2 minus 4, or 6 minus 4 is 2. F of 2 is equal to 2. F of a simply means I want to replace the x with an a. Don't know why you want to do it. Well, you might want to do it if it meant something in particular, like a was going to stand for the number of apples, and b was the number of bananas, and f of x was just f times the number of fruit. Something crazy like that. Anyway, moving forward, function operations. F of x and g of x are any two functions. Remember that we can name, functions aren't always just named f of x. They could be g of x, h of x, v of x, anything of x, or anything of any other variable. Remember that you can add, subtract, multiply, or divide functions to form a new function. You did this when you did polynomials, except that you didn't do it with function notation. So that's the only thing different here, is the function notation. In addition, if I want a new function called h of x, and I want it to be created by adding f of x and g of x, I could put h of x is equal to f of x plus g of x. If f of x is 3x and g of x is x plus 3, then h of x is 3x plus x plus 3, or 4x plus 3. Subtraction, f of x minus g of x. Now here you've got to remember that you are subtracting, you're taking the 3x and you're subtracting all of, this is probably the biggest mistake anybody makes, and that minus must be distributed over the x and over the 3x. So now it's 3x minus x is 2x, minus 3 is minus 3. Multiplication, again, don't forget that you have to distribute the 3x to the x and the 3x to the 3. Probably the biggest mistake when anybody's subtracting or multiplying is the failure to distribute. Distribute the negative in subtraction and distribute everything from the first function to everything in the second function. Now division gets a little bit funny, okay? Division, we can divide f of x by g of x and get h of x. But notice that I have to add in, remember from polynomials time, this is my restriction. I can divide, pretty straightforward, I just put the function of f over the function of g, but then I have to state that x cannot equal -3 because that would make g of x 0, and since g of x represents the denominator, that would make the function, my new function h of x, undefined. The domain of h consists of the x values that are in the domains of both f and g. When h involves division, the domain does not include x values for which the denominator equals 0. Essentially, we're just looking for our restricted values. That's the only real thing that you're doing, and it's only when you've got division, okay? Now, that's all stuff that we've done before. You've played with it before. So what I would like for you to do is take a look at these problems here, okay? Given f of x is equal to 5x squared minus 4x and g of x is 3x plus 1, I'd like you to find f of x plus g of x, f of x minus g of x, f of x times g of x, f of 2 plus g of 3, f of 1 minus g of negative 2, and f of 3 divided by g of 2/3. Go ahead and pause the video here for a moment and try answering these. Okay, now if you're back, let's take a look at this. F of x squared minus 4x plus 3x. Since it's adding, you don't really distribute anything. You're just going to have your 5x squared minus 4 plus 3 means you've got a minus x and then a plus 1. You do not, this can't be factored, but even if it can be, if I'm asking you to do this, this is all you need. Now here, I need to remember to distribute the negative. So I'm going to still have my 5x squared. Minus 4 minus 3 is minus 7. And then I've got another minus 1. Multiplying, I have to distribute. So 5x squared times 3x is going to give me 15x cubed. 5x times 1 is plus 5x squared. And then negative 4 times 3 is minus 12x squared. I'm sorry if I didn't say the x in there. Negative 4x times 1 is minus 4x. Now, combining my like terms, the only like terms I have are here in the middle. So my final answer will be 15x cubed. Positive 5 minus 12 is going to be minus 7x squared minus 4x. Boom. All done. Now, when we do these guys, you're going to plug 2 into f of x, 3 into g of x, evaluate them separately, and then add them together. So 2 squared is 4, times 5 is 20. So over here, I've got 20 minus 8. And then I've got my plus. 3 times 3 is 9, plus 1 is 10. 20 minus 8 is 12, plus my 10 is 22. F of 1. Well, this is 5 times 1, because 1 squared is 1. That's going to be 5 minus 4 is 1, minus 3 times negative 2 is negative 6, plus 1 is negative 5. When I add these together, 1 minus negative makes that plus 5. I get 6. For this one, you're going to plug in the 3 and evaluate, and then plug in the 2/3 and evaluate. So here you're going to get 3 squared is 9. Remember, only the 3 is squared. So you get 9 times 5 is 45. So you've got 45. 4 times 3 is 12. And then in the denominator, you're going to have 3 times 2/3. Okay, here, if you didn't see it, the 3's cancel, which leaves you with 2. Plus 1 is 3. 45 minus 12 is 33. And then that's all over 3, which is going to give you 11, and you're done. Okay? So this is just operations. You've known how to do this forever. You've known function notation, and we did polynomial. We did adding, subtracting, multiplying, and dividing polynomials. So this is really just the exact same thing, but with function notation. Now, something that you have not done before is composition of functions. F of g of x. Please note that this O, this is not times, and it's not fog. It's an open dot. The term composition of functions or composite function refers to the combining of functions in a manner where the output from one function becomes the input for the other. This is a lot of words. We're going to go over it with examples. in math terms, the range, the y values of one function become the domain or x values of the next function. Think of it like this. I have eggs and flour and milk and oil and water and sugar. I've got ingredients. Those are my inputs for my batter. So I input all those individual ingredients into my batter. Then the function is mixing up the batter. I mix up, I stir those. Okay, so I stir those ingredients. What comes out is batter. So input, individual ingredients, stir out batter. I take the batter and I put it into a pan. So the batter is now my input. The function is to bake what comes out as a cake. Okay, so input, you do something to it. The output, you take that, make that input again. Here's another picture. I've got g of x and f of x. The domain of g, I put x in, the range becomes the domain, becomes the range. Okay? Personally, just so you know, I prefer this notation to this notation because this tells me g of x gets put into f of x. Now, here's an example. F of x is equal to x plus 1, g of x is equal to 2x. This says f of g of x. And again, my preferred way of doing this is like this, only because it's a little more visual. It's saying, take this, and every place where there was an x, I'm going to put in 2x. So that's what this means. Now, when I want to do this over the domain of 1, 2, 3, 4, that means I'm going to take 1, 2, 3, 4, and I'm going to put it into g of x. So I'm function g of x. I'm going to pick up the values from the blue area, 1, 2, 3, and 4, multiply them by 2, and drop them off in the yellow area. So 1 times 2 is 2. 2 times 2 is 4. 3 times 2 is 6, and 4 times 2 is 8. So g of x is done. He's done his work. He's dropped off all of his passengers. The range of g of x, these were all the answers I got from g of x, become the input. The new driver, function f of x, is going to pick up these values from the yellow area, add 1, and drop them off in the final green area. So 2 plus 1 is 3, 4 plus 1 is 5, 6 plus 1 is 7, 8 plus 1 is 9. So here's the range. So notice, these got input to g, g output them. The output of g becomes the input for f, which outputs my final answers. Now, if you're working with numbers, that's great, but what if we just want the resulting function? Well, then exactly what I talked about. I'm going to take this and I'm going to plug it in for this guy. So f of g of x is going to become g of x plus 1. G of x is 2x, so 2x plus 1. Boom. I'm done. Now, finding domains of composite functions can be a little tricky. You've got to be careful when a function or the combination of functions contains the variable in the denominator or under a radical. The exceptions on the domain must be stated. So consider these two following. F of x is 1 over x plus 2, and g of x is x over x minus 3. Now, for f of x, x cannot equal negative 2. Easy peasy. G of x, x cannot equal 3. So, what is the domain of f of g of x? Oh, a little trickier. So what I have to do is I have to say, okay, g of x is the first thing, right? Because this is the same thing as f of g of x, right? So, function g of x cannot pick up a 3. He can't pick up a 3. So, this has got to be part of it. Can't pick up a 3. Then, he also has to be careful, because if he picks up somebody who results in a negative 2, f of that person's going to get stranded. That number is going to get stranded in the middle here. Okay? So, here, x cannot equal 3. And when he drops off, okay, he can't drop off. Look at this. He cannot, okay, cannot, I know this is so slow, drop off -2. So in addition to this 3, he can't drop off a -2 because f of x can't pick up a -2. So in general, the domain for a composition will not allow any values restricted by the domain of the starting function, along with any values whose answers from the starting function will be restricted in the second function. So this means that not only can it not pick up 3, but x over x minus 3 cannot equal -2. Okay? So, y plus 2 and not -2. Well, remember, this is what it can't equal. When I solve for my x, I'm going to multiply both sides by x minus 3. So x is equal to -2 times x minus 3. When I distribute, x, oops, that's a not equals, does not equal -2x plus 6. If I add 2x to both sides, I get 3x cannot equal 6. X cannot equal 2. So in addition to the 3, I also cannot pick up a 2, because if G picks up a 2, the answer is going to get stranded here in the middle. Now, y plus 2 and not -2, because this one's -2. Remember that G has a restriction of 3 on its domain, so 3 is also restricted for the composition. F of x has a restriction of -2 on its domain. The domain for f of x is the range of G. This means that g of x has a restriction on its range. The range of g of x cannot be -2. What value or values of x result in g ending in -2? Turns out that it's 2. So the restrictions on the domain of f of g of x are 3 and 2. As long as 2 is not input into g of x, -2 will not try to get into f of x. A little tricky, I know. So, given f of x and g of x, find each one of these, pause the video, and do the work. Okay, hopefully you paused the video and you tried each one of these. I tried to do these a little bit color coordinated. So, you have x minus 2 plus x squared. I simply rewrote it in standard form. The negative, there's no distributing the minus because it's just a single term, so it's -x squared plus x minus 2. Multiplying, you have to make sure that you're multiplying the x squared times the x and the x squared times the minus 2. That's all. Dividing, just a matter of putting one over the other. No, you can't cancel out those x's because there's not an x in every term in the numerator, but you do have to state your restricted value. X cannot equal 0. Down here, f of g of x, I just wrote out f of x, but every place where there was an x, I just left an open parentheses, and then I simply plugged in g of x. So x squared minus 2. G of x, g of f of x, this is just another way of writing it. I put parentheses everywhere where there was an x in g, and then I took and plugged in f of x. Now this is x minus 2 quantity squared, and so I have to FOIL it, and I get x squared minus 4x plus 4. Either this answer or this answer, depending on what the problem is asking you to do. Now, f of g of 3, I personally would calculate g of 3, so I plug a 3 in. 3 squared is 9, so then I put the 9 in. The output from g of 3 becomes the input for f of g of 3, so f of 9 becomes 7. Reversing it, f of 3 is 2. I put the 2 in, and I get 2 squared is 4. Work from the inside out. Now, are you ready for some more practice? Go ahead and try these. You're going to try them, pause the video, and then I'm going to uncover the work and the answers. Ready? F, and again, pause the video, try A, B, C, and D. And you're back. Here, I simply put the 2 in, and then that output became the input for the next one, and you get 11. For B, negative 27. And yes, you can compose a function with itself. Okay? Notice on each one of these, I'm working from the inside out. And finally, f of g of x. At this point, you can pause the video if you got any of these wrong and check the work. If you have problems with these and we're doing distance learning, or for whatever reason you are learning at home, and you can either send me an email, contact me during virtual office hours, or stop by or ask during class. Here, using f of x equals x squared and g of x equals x plus 1, find f of g of x and g of f of x. And note, are these two answers the same? And what would that tell you about the composition of functions? Take a moment and, well, take a moment and do that. I did that right here for you, so you can work it out. You can pause the video and add this to your notes. Are these the same? No, answers are not the same. Therefore, composition of functions is not commutative. It matters which one is on the inside and which one is on the outside. Okay, so it's not commutative. Now, this looks a little crazy, but you've got 3 functions, and we want to know, are the 2 answers the same? Notice that the order is the same. There's no commutative thing going on here. F of g of h of x, f of g of h of x. What is different, however, is over here, I'm going to do f of g of x first, and then the h. Here, I'm doing the g of h first. So, this guy right here is going to become z, and here this is going to become z. So z of x is equal to f of g of x. All right, great. I do that and I get 4x squared. Now I'm going to take the 4x squared and plug it in here. And I get 4. Oops, sorry, I don't plug it in there. Misspeak myself. This is going to be composed of h, so I'm going to take h and plug it into the z, which I do. And this x minus 2 quantity squared gets FOILed. Okay, it gets multiplied x minus 2 times x minus 2, and then the 4 gets distributed. Over here, I'm going to do the g of h of x first. Now, this is going to go into, let me erase this up here so you guys can see that. This is going to go into f. So I'm going to take this and plug it into the x squared, which means I'm going to have to FOIL again. So 2x minus 4 quantity squared winds up being 4x squared minus 16x plus 16. Now, at this point, the results are the same, and it appears that composition may be associative, meaning it might not matter which ones you do first as long as they go in the same order. Please note that just because this worked this way doesn't mean it will always work this way. It does, in fact, work this way. Composition is associative, but this is just an example. This isn't a proof. I want to make sure that you all understand the difference between a proof. A proof shows unequivocally that it will work all the time. This just is an example of it working. You do know it does work all the time. Composition is associative. So, given f of x is equal to x minus 1 over 4 and g of x is equal to 4x minus 3, find f of g of a and f of g of negative b. Well, pause the video and try it. There's g of a. Now I'm going to put that into f of x. Boom, a minus 1. I'm going to put negative b into f. And now I'm going to put f of negative b into g. And voila. So far, so good. Again, bring your questions to me, either through virtual office hours, in-class questions, or via whatever other communication mode is available at the time. Now, this is a tricky one. This is an advanced question. For what value of k is f of g of x equal to g of f of x? So I'm asking what, if any, value would make these commutative. The commutative property does hold, but only for a special instance. So I want to know what value of k would work. So what do? Well, I've got f of g of x. So I'm going to put the x minus 4 over 3 in for the x. Notice I've got the k here. So I find f of g of x. That's x minus 4 plus k. G of f of x. I plug this in, and I get x plus 1/3 k minus 4/3. Now, I want to know what value of k will work. So what do? I set this equal to this. And notice that I have a k here and I have 1/3 k here. I have an x and I have an x. Well, first off, I'm going to multiply everything through by 3 because I got these crazy fractions and I don't want to work with those fractions. So I multiply both sides by 3, and I get 3x minus 12 plus 3k is equal to 3x plus k minus 4. Now I'm not working with fractions. I can subtract 3x from both sides, and lo and behold, the 3x's go away. Now I want to move all of my remaining variables, which is k, to one side. So in this case, I'm going to subtract k from both sides. Then I'm going to add 12 to both sides. Then I'll divide by 2. And it appears that if k is equal to 4, okay, if k is equal to 4, then f of g of x would be equal to g of f of x. Interesting. So there is a case where that would be true, but it's not always true. Commutative is not always true. Now, find the domain of f of g of x. So, for another way, okay, for g of x cannot equal 2. For f of x cannot equal 1. This means there's a restriction on the range of g of x. What value of x will cause the restricted value to be produced by g of x? G of x cannot equal negative 1. So 1 over x minus 2 cannot equal negative 1. Multiply both sides by that denominator. Distribute the negative 1. So negative x plus 2 cannot equal 1. Subtract 2. Divide by negative 1. X cannot equal 1. So in addition to not equaling 2, it cannot equal 1. X cannot equal 1 either. Another way to do it, to check the restrictions on the domain, okay, I can actually do f of g of x, and I've got g of x over g of x plus 1. This is a whole lot more crazy mess. This gets into simplifying complex fractions. But notice when it comes down to it, I have 1 over x minus 1. I find out the 1 here. I also have to be careful because it can't be 2. So for f of g of x cannot equal 1 either. The domain, x is an element of real numbers such that x does not equal 1 or 2. Remember, it can't equal anything that causes problems for g, and g can't output anything that causes problems for f. In summary, addition of two functions can be written a number of different ways. Here's two examples. Subtraction, 2 examples. Multiplication, 2 different examples. Now, please notice it's a closed dot. A closed dot says multiplication. Division, okay, here's 1, 2, 3 different ways. Do not forget, okay, you do need your restricted values when you're doing division. Restricted values. Composition, that's an open dot, okay, not closed. Open means composition. This is really the preferred way. So even if I see it written this way, I would change it to this so that it tells me clearly. I'm going to take whatever g of x is and plug it in every place where there was an x and f. Now, you must indicate restrictions on the domain. Composition is not commutative. Composition is associative. That's it. That's lesson 1, composition of functions.